Question 2 from the 2025 Advanced Higher Physics Examination from the SQA. A fairground ride consists of a rotating drum with a movable floor, and this is shown in figure 2a. You can see the rotating drum, you can see the axis of rotation, and you can see the movable floor. Now, part A says, during a test of the fairground ride, the drum is initially at rest. It then accelerates at 0.12 radians per second every second for 34 seconds. And we've got to calculate the angular velocity of the drum at 34 seconds. Well, we know that the equation for the angular velocity can be written as follows. We can write down omega is equal to omega naught plus alpha t, where omega is the final angular velocity, omega naught is the initial angular velocity, alpha is the angle of angular acceleration, and t is the time. Now we know that omega naught equals 0, so therefore omega is going to equal to 0 plus, put this in a bracket, alpha, the angular acceleration will be 0.12, and we have to multiply it by the time it's going for, 34 seconds, and if we do that on our calculator we get the new angular velocity at 34 seconds, omega equals 4.08, and the units are radians per second. Question 1, Part A, Part 2. The moment of inertia of the ride during the test is 2.4 times 10 to the power 4 kilogram metre squared. Calculate the unbalanced torque required to produce an acceleration of 0.12 radians per second. Well, we know that the torque is equal to the moment of inertia times the angle of acceleration. So all we have to do is put in the numbers and find out the torque is. Torque equals the moment of inertia, which is going to be 2.4 times 10 to the power 4 kilogram metre squared times the angular acceleration, which is going to be times 0.12. And therefore we get the torque, which is measured in Newton meters. If we do that on my calculator, we get an answer of 2880 Newton, and it's going to be meters. So that's going to be the value for the torque to produce that acceleration. Question 2 continued, Part B. The ride is now operated with people standing against the inside wall of the drum. State how the unbalanced torque required to produce an acceleration of 0.12 radians per second every second compares with the value calculated in Part A2. And we have to justify our answer. Well, here we have the situation here. We have got the drum, which as we know is rotating round like that, and it's got a moment of inertia of I. But when you start to have people who have mass at the side of the drum like that, then what's really happening is you're increasing the moment of inertia. So the moment of inertia I has increased. When you have people are standing near the drum, the moment of inertia has increased. Now, according to the equation, the angular acceleration is equal to the torque divided by the moment of inertia. So to keep the angular acceleration the same, and if you have increased the moment of inertia of the drum with the now people at each side, then you have to increase the torque. So to maintain the acceleration, you have to have an increase in the torque. To keep the angular acceleration constant if we increase the moment of inertia. Make this number bigger, you have to make the torque bigger to keep the same ratio, which is going to give you the angular acceleration. So make the torque bigger because there's been an increase in the moment of inertia. Question 2, Part C. When the ride reaches its maximum angular velocity, the movable floor is lowered. The people remain stuck to the wall as shown in figure 2b. You can see the rotating drum, the movable floor, and it's not to scale. Now the rotating drum then slows down and the people slide down the wall. And we've got to explain in terms of forces why the people slide down the wall. Well, let's look at the force diagram acting on that girl stuck to the wall. Obviously, the first force we can recognise is the force due to her weight acting down the way. The weight's acting down the way. Now, there must be an equal and opposite force acting up the way to, in fact, stop her weight accelerating her down the way, and that must come from the force of friction due to her clothes. Now, the other force acting on the person is the push of the wall against the girl's body. Now, the push of the wall is really the contact force, which really is the centripetal force. I'm going to call this the reaction force R. R is the force, this yellow arrow, pushing against the person, and that can be evaluated from using the centripetal force. We know that R will be equal to mv squared, m being the mass of the girl and v being her rotational speed round the way, and of course R being the radius she is away from the centre. Now we do know a link between the frictional force and the normal contact force. Normal because it's at right angles, and it's related to this equation here. Force equals a constant mu times R, R being the force which we've got pushing against the girl of the wall, which is the centripetal force. Now we know that if the velocity decreases, then R is going to decrease. So if the velocity decreases, then we know that we're going to have a decrease in the push against the person's back. That is going to decrease as well. Now if that decreases, then you're going to have this expression up here decreasing, and you're going to get the force decreasing, the frictional force decreasing. And if the frictional force becomes less than the weight, so frictional force becomes less than the weight, then you're going to have the girl accelerating down like that, sliding down the actual wall. So the forces involved here are the weight acting down the way, the frictional force acting up the way, which is related to the centripetal force, which really is caused by the force of the wall acting on the person. And if you reduce the velocity of the rotation, you're going to reduce that contact force. And if you reduce the contact force, you're going to reduce the force of friction, which means the weight will take over if the force of friction falls below the weight, and therefore cause the person to slide down. It's a lot for 1 mark, but that's what's happening.